Hey guys, my name is IBM, and today I bring you another episode of Learning Physics with me. This is essentially Cambridge Physics, and it's supposed to be Physics 9702, paper 4. But of course, the concepts overlap with some other syllabi, such as OCR. You may find the concepts here in Excel, you may find the same concepts in AQ. These lessons or tutorials are entirely designed for making my teaching at school very easy. I can always send my students to my YouTube channel in case I don't have time, and my students can always do self-study or can learn ahead of me, and this makes teaching very easy, and I can teach the whole syllabus in the shortest time possible because students can always do self-study ahead of the lessons. Number two, I also record these lessons because I want my personal kid or my personal child to find them recorded when I retire, because I believe that by the time my child reaches high school, I'll be done with teaching. So those are the major reasons as to why I record these lessons. So if you don't find them attractive or interesting, you can always move on to the other YouTube channels. I don't really care. But nevertheless, without wasting time, by the way, do not forget to download the paper question, past paper questions is the most important thing if you want to excel in this topic of alternating current. I have solved past paper questions, and therefore when you watch them, you'll get more confidence so that you can be able to pass paper 4, having known that is the most important paper for this syllabus or for this subject. Okay, so in lesson 2 of alternating current, I think we shall now go to the second part of alternating current. Remember, in lesson 1, we explored concepts of characteristics of alternating current, and I want us to explore more in lesson 2. Remember, there are 4 major areas which I mentioned in alternating current. You just need to know something about the characteristics of alternating current. You need to know something about transformers, although I'm saying for this curriculum, for those sitting exams this year or next year, you may not have advanced questions about transformers, but because transformers use alternating current, we shall still talk about them. Then the other fourth part was transmission of electricity, and finally we shall talk about rectification. So in lesson 2, I want us to talk about transformers. So let's talk about transformers. Let's explore more on transformers. Remember, like I have said, if you are doing Cambridge paper 4, you may not actually need concepts of transformers in more details, but I will still talk about them here because, like I've mentioned, transformers use concepts of alternating current. Transformers actually use alternating current to do their work. But before we talk about transformers, I want us to remind ourselves of what we did in the previous lesson. We talked about alternating current, where we said it changes direction periodically at a frequency which depends on the generator or on the source. We said we can look at alternating current as electrons or charge carriers moving back and forth. In other words, they were oscillating. That's why we say the graph of current against time was actually following a sinusoidal shape, which gave us an equation of I equals to I naught sine omega t. But remember, current and voltage are directly proportional. This gave us a similar graph for voltage against time, which gave us an equation V is equal to V naught sine omega t. And you recall that, of course, if we were to find the average value of of the current here, the average value of the current was equal to 0, which means also that the average value of voltage was equal to 0. But then, does it therefore mean that if alternating current flows into the wire, there is no power dissipated? For DC values, remember, power is equal to I squared times R. Does it mean that there is no power dissipated because the average current is 0? Not at all. Although the current can be positive or negative for alternating current, the power depends on the current squared. Therefore, the power can never be 0. But remember, the most effective power in a resistor was actually the average power. So we took the average power, we got the average power, and if you recall, we got several expressions for the average power. And I said, if I consider the root mean square values, then whatever I'm getting, I just modify the DC equations by using the root mean square values, and that will be actually the average power. How did I arrive at the root mean square values? I found the squares of this side of the current and the voltage. Then I found the average, and the average of sine squared omega t was a half. So we ended up obtaining I root mean square as I naught over root of 2, and V root mean square as V naught over root of 2. So these equations are going to be very, very important, and you should be able to use such reasoning every time you are doing alternating current. We also saw that the graph of power against time would never go below the x-axis. It was always above the x-axis. Reason: if I consider power as IV, I and V are always in phase. In other words, if I is positive, V is positive, so the product is always positive. If I is negative, V is negative, the product is always positive. So we saw that the graph of power against time is always above the x-axis. And that means the average power is always half of the maximum power. That one, we explored it last time. So I want us now to concentrate on transformers. So I want you to recall that an EMF can be induced in one coil when the current changes in another coil. If you are doing this as a topic before you have studied magnetism and electromagnetic induction, then you should recall your IGCSE concepts. Whenever you have a coil placed next to another coil, if there is a change in current or change in EMF in this coil here, it will create a current in the neighboring coil. That's what you actually call, I think, Faraday's law. You talk about Faraday's law and Lenz's law under electromagnetic induction. So, whenever there is a changing current in one coil, it causes or it induces, it creates, an EMF in a neighboring coil. And it is on this principle that a transformer works. So if this current is alternating, of course, what do we know about alternating? It keeps changing direction. The electrons or the charge carriers move back and forth. So that means the current which is generated in the wire keeps changing direction. Therefore, we call it um, a changing current. So a changing current in a coil will induce an EMF in a neighboring coil. We shall see later on that the only reason as to why it happens from electromagnetic induction is because there is a magnetic field which is created around this coil here, and this magnetic field this magnetic field is cut by the other coil which is neighboring this one. And according to Faraday's law, whenever the magnetic field is intercepted or whenever the magnetic flux is cut, an EMF is going to be induced, as we shall see, or as you have seen in electromagnetic induction. So, if the current is alternating, then the EMF induced is going to be alternating. And this is the principle of the transformer. Now you may be asking yourself, what is a transformer? What is to transform? I think in everyday language, to transform is to change. So the role of a transformer is actually to change. What does it change? A transformer is actually designed to change voltage from a certain level to another level. In other words, it can increase the voltage or it can be designed to decrease the voltage. Therefore, we are going to talk about two types of transformers later on, which you even mentioned in IGCSE, that is the step up and step down transformers. So a transformer is a device which changes, in fact, it transforms. It changes, which it transforms an alternating PD or alternating voltage from one value, that is from one magnitude to another value or to another magnitude. In other words, it can change it from a smaller value to a higher value or from a higher value to a smaller value. If the voltage or the PD is raised to a higher value, the transformer is going to be called step up because the voltage is stepped up. And if it is put to a smaller value, we shall later on call it step down because the voltage has been actually stepped down. So to transform, the transformer's role is to change. It is changing. It is changing the voltage either by increasing its value or by decreasing its value. That is the role of a transformer. And borrowing the ideas of IGCSE, this is how you represented the transformer. I don't show a transformer in details, but I think this is how you represented the transformer. And in electromagnetic induction, you'll talk about the transformer again in a little bit more details, but this is how you represented the transformer in IGCSE, and I don't want to dispute this. However, this is not actually what a transformer looks like, but we should be able to, by now we should be knowing how a transformer really looks like because we find transformers almost on a daily basis in our environments, in our communities, because transformers are used to step down the voltages when they reach our communities because we may be small consumers and we don't need high voltage power supplies. So you might have seen a transformer in real life. However, a transformer has three major parts or four major parts or major important parts. Number one, it has what we call insulated wires which make up what we call the primary coil and insulated wires which make up what we call the secondary coil. And the primary coil and the secondary coil are linked via what we call a laminated soft iron core. Laminated. We shall explore the meaning of the word laminated. In your IGCSE, you know why this is called soft iron. Soft iron is called soft iron to distinguish it from other types of iron because this one can easily be magnetized and demagnetized, which means the magnetic field becomes maximum and decreases to zero. That is magnetization and demagnetization. So, as we shall see how this transformer works, if we have an alternating current as an input, it means the current is going to be changing direction in this coil of wire. And of course, as we shall see or as you have seen by Faraday's law, it will there's a magnetic field around this coil of the wire. There's a magnetic field. But because the current is changing, of course, the magnetic field keeps changing direction. However, this magnetic field spreads into this iron core. But of course, as it continues changing direction, as we are going to see just shortly. So the magnetic field is spreading through the iron core. So the iron core is acting as a link. It is acting as a link. But remember, the primary coil is an insulated wire and the secondary coil is an insulated wire. That means there is no direct contact but the magnetic field can penetrate through an insulator. So the magnetic field spreads through the coil and it cuts or it is intercepted by the other coil on the other side. And by Faraday's law, as we shall see, if the magnetic field here, or which has spread from the left-hand side, it is now here and it is changing direction, but intercepting the secondary coil, by Faraday's law, an EMF is going to be induced. Because what was input was alternating, what we are going to output is also going to be alternating. So there are three major parts of a transformer, that is the primary coil, the secondary coil, and the laminated soft iron core. Of course, the input and output, those are obviously going to be very important because the input is what dictates the output or is what dictates if the transformer will work. So transformers, as we shall emphasize later on, only work with alternating current. So we cannot, because direct current cannot be stepped up or stepped down. So those are the transformers. So to explore more, let me explain this in more details. A simple transformer consists of two coils of insulated wire, which means there is no direct contact between the metallic soft iron core and the wires which are carrying current, because the wires which are carrying current, they could be copper wires, but they are insulated. So a simple transformer consists of two coils of wire. One we have called it the primary, the other one we have called it the secondary. And I'm saying let the number of turns on the primary be NP, and the number of turns of wire on the secondary I've called it NS. Of course, these are linked by a soft iron core as indicated by this diagram here. And I explained why it is called soft iron core. So there is no electrical connection between the primary and the secondary because the wires are insulated. So there is no direct link between, there is no direct contact between the primary and the secondary. However, the soft iron core provides a link for the electromagnetic induction whereby it simply concentrates the magnetic field. The magnetic field has something to spread through so that it reaches the secondary coil. And it is the magnetic field which is going to create a current in the secondary coil by inducing that current in accordance to Faraday's law that we shall explore, or you might have explored, in a unit called electromagnetic induction. According to Faraday's law, uh, according to Faraday's law, the magnitude of the induced EMF is directly proportional to the rate of change of magnetic flux linkage. So a changing magnetic field is equivalent to a change in the magnetic flux. And if the changing magnetic field intercepts wires in a complete circuit, then the changing magnetic field induces an EMF which causes a current in that wire. But I mentioned here that the soft iron core provides a magnetic link, not an electrical link. It is a magnetic link. So like I said in the previous slide, the magnetic link, the magnetic field spreads through this soft iron core easily. But I want you to also note that the magnetic field is everywhere, even outside, around the wire, even outside the core. But remember, this magnetic field keeps changing direction. It keeps changing direction after after every half cycle. It keeps changing direction. That means it is a changing magnetic field. And according to Faraday's law, and whenever we have a changing magnetic field intercepting an a conductor, then an EMF is most likely going to be induced in that conductor. Okay. So briefly, let me give you a clue on how a transformer works. Even though I'm saying for those sitting exams May, June, October, November, or Feb, March 2024, 2025, you may not really find complex questions about transformers or questions which require details of transformers in your paper. But I say these concepts are very important because after all, they link to electromagnetic induction. So briefly, how does a transformer work? So let's briefly discuss the principles of a transformer or how a transformer works. I said you may not really be asked to explain how a transformer works if you are doing Cambridge 9702, but if you are doing a different curriculum, you may be asked to explain how a transformer works. However, it does you no harm if you know how really a transformer works at this level. The principle behind this is actually the principle of electromagnetic induction. So what really happens is that alternating current, or I mean an alternating voltage, is going to be applied to the primary coil. What if we have an alternating voltage, it is going to automatically produce an alternating current. So on the primary, we have an alternating voltage applied, which means it is going to produce an alternating current. A changing voltage is going to produce a changing current in the primary coil. What is the effect of that? If there is a changing current in the primary coil, then there is going to be a changing electromagnetic field or a changing magnetic flux. There is a changing electromagnetic field around the primary. So the alternating current in the primary gives rise to an alternating, when I say alternating, that is changing. It gives rise to an alternating magnetic flux in the core that is in phase when the current with the current in the primary. Of course, if the current changes, the magnetic flux also changes. So the magnetic flux will always change depending on the direction of the current. So that we say they are in phase. So this side of our transformer, we have applied an alternating voltage. It has created an alternating current. The alternating current gives rise to a magnetic field around it, which is changing. Remember, in your concepts of magnetism in IGCSE, you must have noticed that there is always a magnetic field around a current carrying conductor. So if there is a current flowing through a wire, then there's a magnetic field around the wire. If the current keeps changing direction, then the magnetic field also keeps changing direction. So this magnetic flux in the core threads through the secondary. In other words, it spreads from the primary end to the secondary end. So that's why I'm saying this magnetic flux in the core threads through the secondary coil. So it spreads up to the secondary coil. And since the flux is changing, since the magnetic flux is changing, so many times I'll use the word magnetic flux to actually mean magnetic field, because the word flux is just to mean a collection of field lines. It could be an electric flux that we shall see in electric fields. So since the flux is changing, the magnetic field lines keep changing direction. By Faraday's law of electromagnetic induction, an alternating voltage will be induced in the secondary coil. As long as we have a changing magnetic field, then it means by Faraday's law, an alternating voltage is induced in the secondary coil. However, one important thing we need to note is that the induced EMF is proportional to the rate of change of the magnetic flux linkage. That is in accordance to Faraday's law. Thus, the induced EMF will be alternating at the same frequency as the current in the primary coil, but will be out of phase. So in according to Faraday's law, the magnitude of the induced EMF is directly proportional to the rate of change of magnetic flux linkage. So let's say the rate of change of magnetic flux linkage is 5, for example. It means the induced EMF is also going to be proportional to that rate of change. That is in accordance to Faraday's law. If the current in the primary it changes 20 times per second, the induced EMF is also going to change direction 20 times per second. That's what I mean by them having the same frequency, because frequency is the number of cycles per unit time. So The induced EMF will be alternating because the input current or the input EMF is alternating, and it will have the same frequency as the current in the primary. But I'm saying they will be out of phase. To understand why they will be out of phase, then we need to think about Faraday's law. The induced EMF is directly proportional to the rate of change of magnetic flux linkage. When the flux linkage is maximum, the rate of change is zero, which means the induced EMF is going to be zero. And when the flux linkage is zero, it means the rate of change is maximum. Then the induced EMF is going to be maximum. That's what we mean that they are out of phase. They are actually 180 degrees out of phase. So the applied EMF in the primary coil and the induced EMF across the secondary have the same frequency, that is number of cycles per unit time, but they are not in phase. In other words, they will be 180 degrees out of phase. I am saying, according to Faraday's law, an EMF is induced when there is a change in magnetic flux. In fact, the magnitude of the induced EMF is directly proportional to the rate of change of magnetic flux linkage. Remember, when the flux linkage is maximum, the rate of change is zero. That means the induced EMF is going to be zero. And when the flux linkage goes to zero, the rate of change is maximum. So the induced EMF is going to be maximum. That's why we are saying the induced EMF is not in phase with the input EMF. In other words, we say they are 180 degrees out of phase. To understand this concept of them being out of phase, you should now refer to the concepts of electromagnetic induction. If you have not really studied them in school, I'll still record the video of electromagnetic induction later on. But for now, we are only interested in the basic principles of how a transformer works. Number one, an alternating voltage is applied to the primary, which gives rise to an alternating current. The alternating current gives rise to a changing magnetic flux around the primary, which spreads towards the secondary. The changing magnetic flux induces an EMF in the secondary in accordance to Faraday's law. And I'm saying the induced EMF has the same frequency as the primary EMF or the input EMF, but they are out of phase. So that is briefly how a transformer works. So I have a simple animation to demonstrate what I was talking about here. So in the primary, for example, you can see that here this is where we have the input. The input keeps changing direction, that as indicated by this animation, and that means the magnetic field keeps changing also direction as indicated by these black dots. So it means the magnetic field keeps changing direction, and if it is changing direction, we say the magnetic flux is changing. So what does that mean? There will be a current induced in the secondary, which current is also going to be alternating. And I want you to notice from this animation that if the current here is in this direction, the induced EMF is actually in the opposite direction, which means they are actually out of phase. They're actually out of phase. Later on in electromagnetic induction, you now talk about Lenz's law to understand what we are talking about here. Because according to Lenz, the direction of the induced EMF is always such as to cause effects that oppose the change producing it. So the induced EMF and the input EMF are always 180 degrees out of phase. So the changing magnetic field from the primary spreads through the core to the secondary, and as it continues changing, it induces an EMF in the secondary as demonstrated by this. However, I want you to notice there is an arrow on the top of this, which is keeping changing direction, which is representing currents. Because the ionic core itself is a conductor, this is a conductor itself. And the magnetic field is also changing within the core itself. So it means there is also a current generated in the soft ion core itself. As the magnetic field keeps changing direction, the current also keeps changing direction, and that current is what we call eddy current. The eddy current. Actually, it is wrong to say eddy current. It's supposed to always be plural because these currents do not have the same magnitude. So eddy currents grow within the soft iron core, and of course, with the time, you'll find that the soft iron core is warm. In other words, eddy currents dissipate energy in the soft iron core as heat because um, as there is a changing magnetic field inside the core, the changing magnetic field within the core itself would also cause these eddy currents. That means they will dissipate energy in the core as heat. The only way we can reduce these eddy currents, we shall use what we call laminating. We shall talk about laminating later on. But what do we mean by laminating? Compare the size of the eddy currents represented here with the size of the eddy currents represented here. Instead of having just one big plate of soft iron core, we break it into strips, and between several strips, between one strip and the next strip, in between here we put an insulating material. We put an insulating material between the two strips before we put them together, so that the eddy currents, which are gentle, do not grow up, they do not add up to have a very large effect onto the transformer. That's what we shall call laminating later on. But all I wanted people to know is how a transformer works. A changing or an alternating EMF in the primary causes a current in the primary, which gives rise to a magnetic field around the primary. The magnetic field around the primary spreads towards the secondary coil, and the changing magnetic field induces an EMF in the secondary coil. The induced EMF has the same frequency as the input EMF. However, the induced EMF is out of phase, 180 degrees out of phase with the input EMF. During the generation of, during the working of the transformer, because the soft iron core is a conductor, it also, because the soft iron core is a conductor and magnetic field is changing within the soft iron core, it means several currents can also be generated within the core itself. These currents keep changing direction and they have different magnitudes. That's why we call them eddy currents. These waste energy within the core as heat, thereby warming up or increasing the temperature of the soft iron core. So briefly, that is how a transformer works. That is how a transformer works. Okay, so a few things that we need to note now, having known how a transformer works, are the calculations that could be involved. These are the same calculations you did in IGCSE. So remember we said the input voltage, we called it VP, and the output voltage, we called it VS, because the input in the primary is V primary. For the second, we called it V primary. Then the number of turns, of course, the number of turns of the wire of the primary coil, we call it NP. The number of turns on the secondary coil, we shall call it NS. Of course, the current which flows in the primary coil is going to be IP. The current which flows in the secondary coil is going to be IS. So we may be interested in investigating the ratio of the output EMF to the applied EMF, and experiments have shown that the ratio of the output EMF to the applied EMF is dependent on the number of turns. That's how we come up with the step up and step down. If we want a bigger output voltage, then we shall put more turns on the secondary coil than the primary coil. If we want to reduce the output, then we shall put fewer turns on the secondary coil. So when they are generating electrical power from, say, a dam, they will step it up. So the transformer they use has more turns on the secondary coil because they want it to be transmitted at a high voltage. There's a reason as to why. But when the electricity reaches the consumers, which consumers may not use a lot of power, then the electricity is going to be stepped down depending on the consumption. If the consumer is just a smallholder consumer, then it is stepped down to a very small value. But if the consumer is an industry, it may be stepped down, but to a different value from that of an ordinary consumer. So let's consider a transformer with NP turns on the primary coil, IP on the secondary coil. IP as the current in the primary, NS as the number of turns on the secondary, and IS as the current in the secondary, when the EMFs across the coils are Vp and Vs respectively. If this transformer is ideal, if we consider this transformer as being ideal, then we can say it is 100% efficient. What is the meaning of the word ideal? So ideal means practical, it is not achievable, but if we assume it were possible, then it could be possible. But in the real sense, practically it is not possible to have a transformer which is 100% efficient. However, if it were possible, then it will be 100% efficient. And what is this going to imply? It means if the transformer is 100% efficient, the power we input into the transformer is going to be the power we output from the transformer. So when someone asks you to define what you understand by an ideal transformer, it is the one in which the input power is equal to the output power, giving it an efficiency of 100%. So if that is very true, remember by definition of power, energy over time or electrical power was given by I times V. So if the input power is equal to the output power, the input power is the current in the primary times the voltage in the primary. The output power is going to be the current in the secondary times the voltage in the secondary. Therefore, it means that VPIP is going to be equal to VSIS. But remember the ratio of the output EMF, which is of course Vs, is directly or is dependent on the ratio of the number of turns. In fact, they are directly proportional. So the ratio of the number of turns, number of secondary over number of primary, is directly proportional to the voltage in the secondary over the voltage in the primary. So we can simply just combine those three things and say from this equation here, I have that Vs divided by Vp. On the left hand side, I have IP divided by IS from this equation here. But remember, the ratio of the number of turns is directly proportional to the ratio of the voltages. Therefore, when I combine those three, the number of turns of the secondary over number of turns of primary is equal to the voltage of the secondary over voltage of the primary, which is the same as the current, actually, which is the same as the current in the primary over the current in the secondary. So you notice that the current is inversely proportional. The current is inversely proportional here because the equation has been reversed. Vs over Vp is Ip over Is, but the number of turns in the secondary over number of turns in the primary is directly proportional to the voltage of the secondary over voltage of the primary. I want you to note that in practice, actual transformers are they're about 95 to 99% efficient. That means there is some loss in power inside in a transformer. We shall see some of the energy sources, the sources of energy loss within a transformer. But the transformers we use at home, they are not 100% efficient, not at all. So having talked about number of turns, having talked about the ratio of the output EMF being directly proportional or dependent on the number of turns, then this takes us to the fact that there are actually two types of transformers to talk about here. You must have mentioned this in IGCSE. That is the step-up transformer and the step-down transformer. So in case we want the output of the secondary or the output voltage to be greater than the input voltage, we must make the number of turns on the secondary to be greater than the number of turns in the primary. So this results into what we call a step-up transformer. If you want to take down the voltage from the secondary output to be less than the voltage we input in the primary, then we must make sure that the number of turns of the secondary is less than the number of turns in the primary. And this is what we shall call a step-down transformer. So to illustrate this, I've indicated here two diagrams. You notice that if here we have fewer turns on the primary and we have many turns on the secondary. So this is automatically a step up. The output voltage will be greater than the input voltage. Then when you compare this, we have more turns here on the primary and we have just a few turns on the secondary. So this is what we call a step-down transformer because there are fewer turns on the secondary, the output is going to be low. So the output is going to be changed to a low value. So here the transformer is doing its work. It is actually changing the voltage. It is changing the voltage either to a high value or to a lower value depending on the demand. And that is the work of a transformer. It is either to change the voltage to a greater value or to change it to a smaller value. That is what we call the function of a transformer. Okay, so having mentioned that the efficiency of a transformer can never be 100% unless it is just an ideal case. An ideal case means we cannot practically achieve that. We just assume it were possible. So that means we need to explore what really leads to the efficiency not to be 100% in a transformer. So we shall talk about the main sources of energy loss in a transformer. Because the efficiency is not 100%, then we can agree, you and me, that there is energy loss within a transformer. So what are the main energy sources, the main sources of energy loss in a transformer? One of the things I've mentioned was the generation of eddy currents within the core of a transformer, which means not all the changing magnetic field results into an induced EMF in the secondary. Part of the changing magnetic field in the core results into a current within the core itself, which current is wasted as heat within the core itself. So that means energy is being wasted and therefore the efficiency cannot be 100%. That is the most obvious one. Okay, so let's explore the main sources of energy loss in a transformer. In practice, transformers will not be 100% efficient unless it is an ideal condition. So there are several energy losses in a transformer. Number one, which a layman may think about is flux leakage. Now, I'll be talking about linkage and leakage. These two terms always confuse my students. Leakage and linkage. Because I'll be using them almost in the same concepts. Leakage, that is loss to the surrounding or given or escape into the surrounding. Then linkage is from to link. It is like to connect, to lead to. That is linkage. So we have what we call magnetic flux leakage. The purpose of the soft iron core is to reduce this leakage by providing a link. But still, the magnetic flux is all around the primary coil. So it means not all of it is within the core. All of it, not all of it will be only within the core. It spreads all around the primary coil. So when we talk about flux leakage, when the changing flux from the primary threads to the secondary coil, some of the flux is not spreading through the core. So it means we have what we call a leakage. That's what we call magnetic flux leakage. This leakage therefore means, or this leakage therefore means that there is loss of magnetic flux between the primary and the secondary coil as it flows back and forth. Part of it spreads to the surrounding rather than into the core, rather than through the core. So there is loss of magnetic flux between the primary and the secondary coils as the flux spreads, as the flux moves back and forth or flows back and forth. So this loss means that the input power is essentially not going to be the same as the output power. How is this minimized, by the way? In designing transformers, of course, these power losses are going to be minimized. We have what we call an ion core, which we have already talked about. Why is there an ion core between the primary and the second? Why don't we just have coils like that hanging in space, but instead we put an ion core between the primary and the secondary? By the way, even without an ion core, there will be an induced EMF. But why do we have an ion core there? The role of the ion core is to reduce flux loss, increasing flux linkage. Like I said, I will be using the two terms almost in the same concepts. There's flux leakage and there's flux linkage. So the ion core increases flux linkage, it reduces flux leakage. So it reduces flux leakage, but as it increases flux linkage with the secondary. So the soft ion core, its role is to actually increase the flux linkage or to reduce the flux loss, or to reduce the flux linkage. To reduce the flux leakage. But now look at the design of the soft ion core. It is designed in a continuous loop or in a closed loop. It is not by mistake. So the core is designed to maximize. The core is designed for maximum flux linkage. So we shall say it concentrates the magnetic flux linkage. So the ion core forms a closed loop, and the primary and the secondary coils are wound on each other. In most transformers, you find that this is the strip of the soft ion core where we have the primary on it, and at the same time, we have the secondary wound onto the same. After all, these are insulated wires. So you have on the same strip, let me use a different color. On the same strip, you have the primary one, and you also have the secondary one. So you have the secondary, and on this side you have the primary. So this is trying to maximize the flux linkage, to concentrate the flux linkage, to minimize the flux loss. So this design ensures that all magnetic flux produced by the primary coil passes through the secondary. So we basically say the purpose of the soft ion core is to concentrate the magnetic flux linkage, to concentrate the magnetic flux linkage. That is the purpose of the soft ion core. So the source of energy loss is flux leakage. I said what we mean by flux leakage. This is loss of magnetic flux between the primary and the secondary coils as it flows back and forth. Part of it spreads to the surrounding without being connected directly or without reaching the secondary. And that loss is going to lead to less power being generated. Okay. Number two, another source of energy loss is there's what we call resistive heating in the primary and the secondary coils. Because these are wires, they have some resistance. Anything which has resistance, if a current flows through it, then there is some power dissipated within it. So some power is dissipated within the coils, the primary and secondary coils, because they have some resistance. So this power dissipated due to the resistance in the primary and the secondary coil results into the output power being less than the input power, making the transformer not to be 100% efficient. Well, this could be slightly minimized. Instead of using any ordinary wires, Many times, low resistance thick copper wires are used for the coils. That is just to try and minimize heat loss due to heating, power loss due to heating or resistive heating in the primary and the secondary coils. Okay, more sources of energy loss. Number three is heating of the core due to eddy currents. I've already talked about eddy currents here. Due to a changing magnetic field within the core itself, the changing flux in the core will cause an induced current in the core itself, and that induced current in the core is what we called eddy currents. The eddy currents in the core, of course, will cause heat because the core has some resistance. So if these eddy currents are flowing within the core, and remember they keep changing directions too, they cause the core to warm up. So energy is wasted due to eddy current heating of the core. That is the third source of energy loss. But this one can be minimized by using what I call laminating. What do you mean by laminating? I mentioned and I demonstrated that laminating involves putting insulators between strips which make up the soft iron core. Putting insulating materials between strips that make up the soft iron core. I'm going to demonstrate what we call laminating later on. Okay, so building up the core from thin strips of soft iron which are electrically insulated from one another. This one reduces energy loss as thermal energy due to eddy current. So eddy currents cannot build up because the eddy currents within one strip cannot add up to eddy currents in the neighboring strip because there is an uninsulating material between them. So this minimizes or reduces heat loss due to eddy current. One important thing I want you to note is that laminating does not stop. Laminating the core cannot prevent or stop eddy currents from forming, but it just reduces the energy losses by reducing the sizes of the currents. Instead of the currents adding up to give a very large heating effect, the eddy currents in one strip do not add up to the eddy currents in the neighboring strip. So this minimizes the amount of heat loss due to these eddy currents. Number four, and the last one, is going to be hysteresis loss. During a generation of induced EMF, which is alternating, there is continuous magnetization and demagnetization of the core as the magnetic field keeps changing direction. The magnetic flux linkage grows to the maximum and it grows to zero as there is a change in direction. In the process, there is continuous magnetization of the core and demagnetization, continuous creating of a magnetic field and cancelling out of the magnetic field. This continuous magnetization and demagnetization, or this repeated magnetization and demagnetizations, wastes energy in the core as heat. This is what we call hysteresis loss. The continuous magnetization and demagnetization is what we call hysteresis loss. So many times we can account for the use of soft iron core to be the one responsible for reducing heat due to hysteresis or due to repeated magnetization and demagnetization. However, remember iron is an electrical conductor. Since iron is an electrical conductor, or since iron, an electrical conductor, is used as the material for the core so that the magnetic flux linkage is concentrated or is large, eddy currents cannot be prevented. We can just minimize them. We can also not avoid using iron because we need continuous magnetization and demagnetization. So it means the heat loss due to hysteresis may not really be avoided at all. that using soft iron, which can easily gain magnetism and very easily and rapidly lose magnetism, we kind of minimize hysteresis loss, but not to a large extent. We cannot avoid using soft iron in this case because it magnetizes and demagnetizes very fast. But if we cannot avoid using soft iron, then we cannot avoid eddy currents. The only thing we can do with eddy currents is we can minimize their effect. So before we leave this, let's understand what we mean by laminating in more details using a simple diagram here. So these are strips of soft iron 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So I have 11 strips of soft iron here. So what we mean by laminating is that between each of these strips, we put an insulating material. It could be rubber, it could be wood. Between each of these strips, we put an insulating material. Then we now bind them together and then put the primary and the secondary coil, the second and the primary coils on them, so that if eddy currents grow on this first strip, they do not they don't add on to the eddy currents on the neighboring strip, and the process continues, so that heating effect due to a build up of eddy currents is minimized. But if we were just having a single strip like this one here, then eddy currents would add up, or eddy currents would be large enough to cause a very large heating effect. So this is preferred as compared to this one here, because this one prevents eddy currents from summing up to cause a large heating effect. That's what we call laminating. Okay, I think I've said a lot, so I think we need to do a few examples. Example number 1, a transformer. A transformer is to be used with an alternating supply of 240 volts to power a lamp rated at 12 volts, 3 amperes. The secondary coil of the transformer has 80 turns. So a transformer is to be used with an alternating supply. So this is going to be V in the primary to power a lamp rated at 12 volts. So this is going to be the output. So this is V in the secondary. I 3 amperes, this is going to be the current in the secondary. The secondary coil of the transformer has 80 turns, so this is going to be number of turns on the secondary. Assume that the transformer is ideal. This means the efficiency is 100%, so the input power is the same as the output power. Therefore, the equation Ns over Np equals to Vs over Vp, which is equal to Ip. This is where students make a mistake. Ip over Is. The currents are in the reciprocals. You can always remember that by just saying Vs times Is equals to Vp times Ip. When you try to divide the equations, you notice that Vs over Vp is Ip over Is. So assume that the transformer is ideal. Calculate for the primary coil the number of turns, the current. So every time we use this equation here, we must be assuming that the transformer is ideal. So to start with the number of turns, the number of turns in the secondary over number of turns in the primary is equal to the number of turns, it is equal to the voltage in the secondary over the voltage in the primary. Now the reason as to why alternating current is going to, or characteristics of alternating current are going to be very important is that one of these values could be given in peak or root mean square values. So if they are given as root mean square values, that means V secondary should be root mean square, V primary should also be root mean square. If they have given you peak values, V primary should be peak value, V secondary should also be peak value, so that there is uniformity. So by simple substitution, we have that the number of, or making number of turns the subject in the primary is going to be number of turns in the secondary times voltage in the primary divided by voltage in the secondary. When I substitute here, I'll have 80 times 240 divided by 3. No, not 3, divided by 12. So I'll press my calculator very fast. 80 times 240 divided by 12. So this is 1600. Then this is the first part of the question. Then the second part of the question wants us to find the current. So for the current, for the primary coil, the number of turns, the current. So the current in the primary divided by the current in the secondary is equal to the voltage in the secondary divided by the voltage in the primary. It is the reciprocal. So the current in the primary is going to be voltage in the secondary, which is 12, voltage in the primary, which is 240, times current in the secondary, which is 3. So you have, I think, 3 times 12, that is 36 divided by 240. So the current in the primary is going to be 0.15 amperes. Okay. A radio requires 6.0 volt supply, but has to be operated from a 230 volts main supply. So this is going to, because this is what is required, this is going to be the voltage which we must get from the secondary. So this is going to be the voltage we must put into the primary. It is fitted with a transformer to reduce the mains voltage. Calculate the turns ratio for this transformer. If the primary coil has 5,000 turns, how many turns must the secondary have? So we want to first calculate the voltage. Calculate the turns ratio, that is the ratio of the turns. If the primary coil has 5,000 turns, so number of turns on the secondary divided by number of turns on the primary should be the same as the voltage in the secondary over the voltage in the primary. So the turns ratio, this is the turns ratio. The turns ratio is going to be, if I start with the secondary, the turns ratio is going to be 6 divided by 230, which is going to be 6 divided by 230. So this is going to be 0.026. It could be the other way around. The examiner would specify the conditions they want you to calculate this. It could be 230 over 6. It could be number of turns in the primary over number of turns in the secondary, but this is not specific. Then the ratio, so that is the turns ratio. This is the turns ratio. And we notice that the ratio is less than 1. So that means this is going to be a step down transformer. The voltage is going to be reduced. Then how many turns must the secondary have? So because this is the turns ratio, I'll simply say number of turns of the secondary over 5,000 for the primary should be equal to the turns ratio, which is 6 divided by 230. So you just cross multiply. Number of turns of the secondary is going to be 6 times 5,000 divided by 230. So this is approximately 130 because it should be a whole number. So the secondary coil has 130 turns. I think if you check very carefully, you notice that this is reasonable because the voltage has to be reduced by a factor of about 230 divided by 6. That is a factor of about 40, I think, because approximately 40. So because the secondary voltage has to be reduced by a factor of approximately 40, then I think it makes sense for the number of turns to be approximately 5,000 divided by 140 to be approximately 130. Because let me see, 5,000 divided by 40, 5,000 divided by 40. It's approximate, it's 125, which is approximately 130. Okay. So here we have two transformers. What is the turns ratio of the step up transformer in the figure above? Number of turns. Let me try to count the number of turns in the secondary. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So the ratio is here. This is 15 divided by 1, 2, 3, 4, 5 divided by 5. That is approximately 3. That is the turns ratio. The ratio of the secondary to the primary. Then what is the turns ratio of the step down transformer in the figure above? So step down, we have 1, 2, 3, 4. So we have 4 divided by 1, 2, 3, 4, 5, 6, 7, 8. So 4 divided by 8, this is going to be 0.5. So the turns ratio here is 0.5. If an alternating PD of value 10.0 volts is connected across the primary coil of each, what will be the induced EMF across the secondary? So we want to find the induced EMF across the secondary for each. If the input in the primary is 10 volts. So now that we have the turns ratio, so we want the induced EMF from the secondary. So the turns ratio is number of turns on the secondary over number of turns on the primary is equal to voltage in the secondary over voltage in the primary. So it means the voltage in the secondary is going to be the turns ratio, which is this one here, times the voltage in the primary. So this is going to be 10 times 3, which is going to be 30 volts. And here voltage in the second is going to be 0.5 times 10. Because the turns ratio is 0.5, then the input is 10. So this is going to be 5 volts. So you can easily see that this is step down and this is step up. A power station generates electricity at a voltage of 25 kilovolts. This must be transformed for onward transmission at 400 kilovolts. If the primary coil of the transformer used has 2000 turns, how many turns must the secondary coil have? Okay, I think this is an easy. Some of these questions really look like IGCS equations because they are direct, but it's good to practice using the equation for an ideal transformer. If the primary coil of the transformer used has 2000 turns, how many turns must the secondary coil have? So number of turns in the secondary over number of turns in the primary is equal to the voltage of the secondary over the voltage of the primary. So they told us that the primary has 2000. What will be the secondary? So number of turns of the second is going to be voltage. A power station generates electricity at this voltage. This must be transformed. This must be transformed for onward transmission at this. So this should be the input from the transformer. So voltage of the secondary is going to be 4000 kilovolts and voltage of the primary is 25 kilovolts. So this is times the number of turns on the primary, which is 2000. So I'll just check my calculator. 400 times 2000 divided by 25. So this gives us 32,000. Example number 5. A step-up transformer has turns ratio 10 to 1 when an alternating PD of 20 volts is connected across the primary coil. A current of 50 milliamperes flows in it. Calculate the values of the PD across the secondary coil and the current flowing in it. Assume no power is lost in the transformer. So it is a step up. So it means it has 10, the number of turns of the secondary over the number of turns of the primary is going to be 10 over 1. It is 10 to 1. When an alternating PD of 20 volts is connected across the primary coil, a current of 50 milliamperes flows in it. Calculate the values of the PD across the secondary. So remember, number of turns of the secondary over number of turns of the primary is equal to voltage in the secondary over voltage in the primary. So we want the PD across the secondary, yet the PD in the primary is 20. So this implies that voltage in the secondary is going to be 10 times voltage in the primary, which is 20, and this is 200 volts. Then, and the current flowing in it, assume no power is lost in the transformer, so the transformer is ideal. So we want to find the current. So for the current, we shall still say voltage. I can still use the number of turns, but I'll use voltage. So I'll say voltage in the secondary over voltage in the primary is equal to the reciprocal of the currents, I in the primary over I in the secondary. So this implies that the voltage in the secondary is 200, voltage in the primary is 20, which is the same as 10 over 1, is equal to I in the primary, which is 50 milliamperes, divided by I in the secondary, which is not known. I'll just cross multiply. So this implies that the current in the secondary is going to be equal to 50 times 20. Remember, this is still in milliamperes, divided by 200. So 1000, that is 10 over 2, which is 5. In practice, the secondary PD is found to be 180 volts and the secondary current is 4.5 milliamperes. In practice, the secondary PD is found to be 180 and the secondary current is 4.5 milliamperes. That is in practice. The other one was theoretical. What percentage of the power is wasted in the transformer? What percentage of power is wasted in the transformer? So theoretically, the power is, I'll call it power 1. So power is going to be equal to I times V, and this is going to be equal to I. So in practice, this is going to be equal to 4.5 times V, which is 120. So this is in practice. So this power is this power is 4.5 times 180. So this power is 810 watts. This is not power 1, this is going to be power from the secondary. Then the power in the primary is going to be the current in the primary, which is 50 times 10 to the power of minus 3. This was milli. There's a times 10 to the power of minus 3 here. So times 1 exponent minus 3. So this is 0.81. Then the other one is 50 times 10 to the power of minus 3 times V in the primary, which was 20. And this is 50 exponent minus 3 times 20. So this is 1.0 watts. So percentage loss is going to be 1.0 minus 0.81 divided by 1.0 times 100. So this is going to be 19%. Okay. So this is the power from the secondary in practice. This is the power from the primary. And then we get the difference. Percentage loss is approximately 19%. Okay. I think most of the remaining questions can be solved by most of the students, but I'll just give a hint. So the table below shows information about 3 transformers. Copy and complete the table. Assume no power is lost. Assume there is no power lost in the transformer. So if we assume no power loss in the transformer, then the transformer is ideal. Therefore, you just use I in the primary over I in the secondary. Number of turns in the primary over number of turns in the secondary is the same as V in the primary over V in the secondary, which is the same as I in the secondary over I in the primary. The currents are the reciprocals. The currents are inversely proportional to the PDs in this case for an ideal transformer. So you just use, for example, if I have number of turns in the primary, a number of turns in the secondary, voltage in the primary, I want voltage in the secondary, I stop here and I substitute to get this. Then the current in the primary is given. You want the current in the secondary, you can now take this and find this. Then for the power, of course, for the power, you can just multiply either I in the secondary times V in the secondary, which is the same as I. So this is the same as I in the primary times V in the primary, because this is an ideal transformer. So you just get I in the primary. For example, I can know if I have I in the primary and V in the primary, it means the power here is automatically going to be 230. The power here is also 230. The power here is 0.12 times 0.6.2. I think that is 6. Is it 6? No. 12 times 0.2. That is 2.4. These ones are easy to find. So you can use the equation to find the number of turns, the missing currents, and complete that table. The primary coil of an ideal transformer has 1,200 turns and is connected to a 240 volts alternating supply. The transformer is to be used to step down the voltage to 9 volts. So this is voltage in the primary, this is voltage in the secondary, this is number of turns on the primary. So you need to find the number of turns on the secondary. That one is direct. An appliance rated as 9 volts, 1.5 amperes. So this is going to be voltage from the secondary, the output of the transformer. This is going to be current from the secondary. It's connected to a secondary coil of the transformer. Calculate the current in the primary coil. Calculate the current in the primary coil. So, of course, the number of turns, it is the same, it is part of the same question. So the number of turns, you have the ratio of the number of turns, so you should be able to find the current in the primary coil. An ideal transformer is to be used to step up a voltage from 220 volts to a current of 15 milliamperes at 6.6 kilovolts. So this is current of the secondary, voltage of the secondary. The primary coil has 250 turns, so this is number of turns of the primary. So this was voltage of the primary. So you should be able to use the equation that we have just stated to find the ratio of the number of turns on the secondary to that on the primary, the number of turns on the secondary coil, the current in the primary coil. Of course, for the ratio of the number of turns, you just divide V secondary divided by V primary. You get the ratio of the number of turns. Then, of course, the ratio of the number of turns is equal to the ratio of the voltages. So if I know the ratio of the voltages and I know the number of turns of the primary, I just substitute in the equation. Number of turns in the secondary over number of turns in the primary is equal to voltage of the secondary over voltage of the primary, which is the same as I in the primary over I in the secondary. So we're just using that simple equation to solve that question. Lastly, you should be able to explain why the core is made up of iron. And many people think when they say, why is the core made up of iron? Immediately they will say iron is a good conductor. But that is not really the most important explanation as to why the core is made up of iron. The purpose of the soft iron core is to concentrate the magnetic flux linkage, and iron can easily be magnetized and demagnetized. That's why we call it soft iron. Explain why thermal energy is generated in the core. We talked about eddy currents. The changing magnetic field induces eddy currents in the soft iron core, which dissipate energy as heat. Explain why input alternating voltage is used rather than direct voltage. Why do we use alternating current in a transformer rather than DC? We know that alternating current can easily be stepped up and stepped down using the transformer. Direct current cannot be stepped up or stepped down. But what is very important about the alternating current as being used in transformers, because transformers only work with alternating current since direct voltages produce a constant magnetic field. Direct voltage produces a constant magnetic field, and according to Faraday's law, a constant magnetic field cannot induce a current or cannot induce an EMF. So a constant magnetic field will not produce a changing magnetic field. So a constant direct voltage which produces a constant magnetic field. And if we have a constant magnetic field which is not changing, then the induced EMF is going to be zero. Explain how a current in the primary gives rise to an induced EMF. So this one is like equivalent to explaining how a transformer works. Explain why an EMF is not induced when the direct voltage is used. We have already explained this one here. Direct voltage creates a constant magnetic field, and an EMF cannot be induced when we have a constant magnetic field. So that is the part of a transformer. Those are the basic concepts that we needed to talk about under a transformer. And like I said, you may not find a detailed equation about a transformer in the new topic, the new syllabus, but you may find some concepts, some knowledge, or some questions that require some knowledge about the transformer. Let's look at the second last part, and that is transmission of electrical energy. Transmission of electrical energy. While talking about the transformer, we have mentioned that during the generation of electricity, electricity is generated at a certain power, but if it is to be transmitted to a long distance, it is going to be stepped up to higher voltages so that it is transmitted at a high voltage. So transmission is achieved on high voltage, and there is a reason. What is the reason behind that? So transformers play an essential part in the transmission of electricity because we know power plants are usually placed from towns. Dams are not really normally constructed in towns, but yet electricity is needed in towns, and sometimes electricity is needed to be moved to longer distances. In my country, electricity generated from the dam travels across borders to even neighboring countries. So since the wires have some resistance, we expect that if electricity is being transmitted or if power is being transmitted through the connecting wires or the transmission lines, power is going to be wasted because if there is a resistance and there is a current, then power is lost, which loss in power is given by I squared times R, where I is the current flowing through the transmission lines and R is the resistance of the transmission lines. However, it turns out that this loss is going to be reduced if the power is transmitted at a high voltage. So instead of transmitting power at low voltage, it turns out that the power transmission is going to be reduced. If we transmit a certain power but at a high voltage, it turns out that the power loss is minimized. How is that possible? To understand how the power loss is minimized, let's consider this example here. A small town in your village, a small town in your country, which could be several kilometers away from a dam or from an electricity generating station, may require 120 kilowatts of power on average. This is what is required. Therefore, this is what should be transmitted to reach them. But the total resistance of the transmission lines which are available for use is 0.4 ohms. Let's calculate the power loss if the transmission is 1 made at 240 volts and 2 made at 24,000 volts, and then we compare which one is advantageous. Is it A or it is B? Let's start with A. I'll put A this side. Transmitting power at 240 volts. What can we observe here? So first of all, let's find the current which flows. The current which flows in the transmission lines is going to be power divided by V. The power which should be transmitted is 120 kilowatts, that is 120 times 10 to the power of 3, but it's going to be transmitted at a voltage of 240 volts. So this gives us, I think that is a half, which is 500 amperes. So the power, if we transmit the power of 120, if we transmit the power of 120 kilowatts at 240 volts, this is the current which flows in the wires. On the other side, if we transmit, this is 24,000 volts. If we transmit the same power, 120 kilowatts, at a voltage of 24,000, what current flows? So the current flowing is I equals P over V, which is going to be 120,000, 120 times 10 to the power of 3 divided by 24,000. I think this is, isn't this 5? 120,000. So I remain with 120 divided by 24, which is 5, I think. So this is going to be 5.0 amperes. So do we notice that if we transmit the same power at a high voltage, the current which flows through the connecting wires is smaller than transmitting the same power at a lower voltage? Let's check the power loss. So power loss, how much power is lost then? Power loss is given by I squared times R. In this case, it is going to be 500 squared times R, which is 0.4. So this gives us 500 squared times 0.4. So this is giving us 100 kilowatts. So this is 100 kilowatts being lost. But remember, the town requires 120. If 100 is lost, it means the town will only receive 20 kilowatts. Let's check the other side, the power loss. If we have transmitted the power at high voltage, in other words, if we have stepped up before transmission, so here the power loss is going to be equal to I squared, which is 5 squared times R, which is 0.4. So I squared times, so it is 25 times 0.5. I think this is 10. 25, I mean, yes, 25 times 0.4 must be 10. 10 watts. So notice that the town wanted 120 kilowatts. So if we transmit the power to 24,000, it's only 10 watts which is being lost. So of course 10 watts is almost less than 10% of what is required. But 100 kilowatts is almost 80% of what is required. So it means in this case, it is disadvantageous to transmit power at a low voltage. That's why it is going to be stepped up. And this is one major advantage of transmitting power. I mean, it's one major advantage of alternating current. It is easy to step it up for long distance transmission because if we transmit it at high voltage, the current flowing is very small and the power loss is going to be low. This is very economical. This is extremely economical. Maybe that is not satisfying. Let's check another example before we make a conclusion. A power station generates electrical power at a rate of 10 megawatts. The power is to be transmitted along cables whose total resistance is 10 ohms. Calculate the power losses in the cable if the power is transmitted at 50 kilovolts and at 250 kilovolts. So let's have 50 kilovolts here, and we shall have 250 kilovolts the other side. So first of all, let's find what current flows if we transmit at 50 kilovolts. So here the current flowing is going to be 10 times 10 to the power of 6, that is mega, divided by 50 times 10 to the power of 3. I'm using I equals to power divided by V. So I think this is 10 divided by 5, that is 2. So this is going to be 200, I think, amperes. And on the other side, the current which flows is going to be equal to 10 times 10 to the power of 6 divided by 250 times 10 to the power of 3. 100 divided by 3, 250, I think that is 4. So this is 40. So this is going to be 40 amperes. So you notice at high voltage, the current flowing is low. At low voltage, the current flowing is high. If you check the power loss, so the power loss here, remember it is I squared times R. So it is going to be 200 squared times the resistance, which is 10. So 200 squared times 10. So this is giving me 400,000 watts. So 400,000 watts is lost. This is almost 400,000 divided by 10 times 10 to the power of 6 times 100. What percentage is this? divide by 10 exponent 6 times 100. So this is almost 4%. 4% is being lost. So this is 4%, almost 4%, which is being lost. Is it 4%? 400,000 times 100 divided by 10 millions. It's 4%. On the other side, the power loss is going to be I squared, which is 40 squared, then times 10, which is going to be 40 squared times 10, which is 16,000. As a percentage, it will be 16,000 divided by 10 times 10 to the power of 6 times 100 to change it to percentage. So this is 16,000 times 100 divided by 10 exponent 6. So here what is lost is 0.16%. So you notice that in all cases, a small fraction or a small percentage of power is lost if we transmit it at a very high voltage. So I therefore want you to note the following. Number one, the advantage of transmitting power at high voltage is now very, very, very obvious. The advantage of transmitting power at a high voltage is now very obvious. And how is it obvious? We have seen that at high voltage, the current flowing in the cables is very small, thus the power dissipated in the cables is minimum, or the power loss in the cables is minimum. So there is a much less power loss at high voltages. At high voltages, the power loss in the cable is very small because the current flowing is very small. And the advantage of using alternating current rather than direct current is that an alternating current supply can efficiently be stepped up, in other words, raised to a higher voltage for transmission using a transformer, so that the current which flows in the cables is reduced, and if the current flowing is reduced, then the power loss is going to be reduced. That is the major advantage of alternating current. It can be stepped up to high voltage so that the current flowing into the transmission lines is smaller, which means the power loss in the cables is smaller. This makes it economical for long distance transmissions. One important thing you need to note very carefully is that transformers only work with alternating current, because transformers rely on induced EMF. They rely on magnetic flux change or change in magnetic flux. And direct voltage or direct current cannot produce a changing magnetic flux. Direct current or direct voltage only produce a constant magnetic flux. So we cannot use DC on transformers. You cannot connect a battery or a cell on a transformer. By the way, you should also note that generators only produce alternating voltage. Generators only produce alternating voltage because of the principles which are used during the generation of this voltage. As the coil turns, it changes direction, the induced EMF or the generated EMF also keeps changing direction. So generators only produce alternating voltage, and transformers only work with alternating current or alternating voltage. Finally, the final note we need to have here: transformers used in transmission networks have very high efficiencies. I said it is between 95 to 98. So transmission of AC is also more efficient than DC. So transmitting alternating current, because transformers are relatively high, they have high efficiency. So it means transmission of alternating current is normally more efficient than transmission of DC. Imagine you produce DC in a certain town and you transmit it to another town. And remember this, it is not possible to step it up or step it down. It just goes the way it is. The power loss is going to be high. So that means transmission of alternating current is more efficient. Okay. So I have miscellaneous notes that people need to note, but they are not really very, very important for this level. Electricity is sent over long distances using cables. Those are connecting lines. Therefore, before transmission from the generating station, the alternating voltage is stepped up to an excess of about 200 kilovolts. We have now known why it is stepped up. Then after transmission, when it reaches its destination, it is going to be stepped down. The final voltage will depend on what the consumer really wants. If the consumer is a smallholder consumer, the voltage is stepped down to a certain value. If the consumer is an industry, the value is stepped down but to a relatively higher value than that of an ordinary consumer. And if a high voltage and low current transmission of electrical power, in high voltage and low current transmission of electrical power, low currents will also require thinner and therefore cheaper cables. So if now the current flowing, since we have transmitted power at a high voltage, the current flowing is low, then it means we can use the thinner cables. Which thinner cables are even cheaper? The thinner cables are even cheaper because the material will be less. Also, I want you to note that the energy loss in the transmission cables can also be reduced by reducing the resistance of the cables themselves. But of course, I want you to note this very carefully. Large reductions in the resistance of the cables can only be brought about by making the cables very thick. Remember from your concepts of electricity, resistance is inversely proportional to cross-sectional area. If you want to have a smaller resistance of the cables, then they should be thicker. They should have a greater cross-sectional area. Because if the cross-sectional area is bigger, the resistance is going to be smaller. But of course, this one is not practical and it is rare done for several reasons. If we use thicker cables, then it means thicker cables are going to be very expensive because they require more material to make. That's why that is not a practical reason as to why thicker cables should be used. And number two, if the cables are thicker, insulating them would be relatively very expensive and more difficult. So it's more difficult and costly to insulate high voltage cables than to be laid underground because we can't lay them underground without insulating them. If we have large high voltage cables, then it would also mean, because if they are large high voltage, then it will also mean that we have to insulate them very well and before we lay them underground, because we can't lay them underground without insulating them. This also increases the cost. So those are the basics under transformers and the concepts of transmission of electrical power. In summary, we said we explored how transformers work. We mentioned step up and step down transformers. We saw the equation, the over-ideal transformer, and we saw why electricity is transmitted at high voltage. Those are the basics that we had to pick in this lesson. Until next time, bye bye.